This is a video for AQA Discrete Mathematics. This is Graphs and Networks section 2.4, where we're looking at practical problems concerning the TSP, so travelling salesperson problem. Well, the first thing to consider is how does what we call a practical problem differ from the classical problems that we've dealt with in earlier videos. You remember that in the classical problem we have a complete network where each of the arcs represents the least weight joining the two vertices at the end of the arc. In practice, then a couple of things are different. We may not necessarily have a complete network, so it's not necessarily going to be the case that every single node is joined to every other node. And the second thing is there may be a direct arc between two nodes, but it may not be the least weight or the shortest path between those two nodes. Now, a simple example of this would be to consider, say, two towns A and B joined by a country road, and then a third town C between them, but there's a motorway going from A to C and another motorway going from C to B. So in terms of time, if that's what we're interested in, the time to get from A to B, the least time would be to go from A to C and then from C to B. So there's an example of where in practice you may not have what we call the triangle inequality. That is that the direct side is going to be greater than the sum of the other two sides. So this is in violation of what's called the triangle inequality. But it's possible to turn this practical problem into a classical one by simply constructing a new network which is complete and has the arcs all with the shortest or the least weight between the direct path for the nodes. Now this we normally do by considering a matrix. So it may not be complete, and you can see here we've got an example which is definitely not complete. So there's no direct link from E to B, for example. And also we have a situation where the arcs direct, for example, from N to M is 283, but we can see that if we went from M to N via L, we've got there a total of 236, which is definitely less. So putting this all into a matrix, then you get the following, and just going over one or two of the points there, then from B to E, that 230 there, although it says B to E, is actually from B to L and then from L to E. The 236 from N to M, although there is a direct link from N to M, this one is actually going from N to L to M. But there we've got a new network. We don't need to draw it. We've got a matrix, and we know that we can then use our methods for travelling salesperson problem to work out an upper bound and a lower bounds for this network using the table. So let's use the nearest neighbour algorithm starting at B to work out an upper bound. So remember the nearest neighbour, what we do is we put a 1 in the column for B, find the shortest path, which is 82, having deleted then the rows for B and L. That gives us L as being our second node to consider, and remember then we look at L only, so we want then the shortest path from L, and that's to N. Now it's worth keeping track of this, so we're going from B to L and then from L to N, so N becomes the third one, having deleted the row, and from there we get the shortest there is 236, so that gives us 2M. So from the fourth one, M, we can then go to E, 244, and then finally we've got to get back to B, so we get the 230, getting us back to B. So there's our route, B, L, N, M, E, B, and if you total up the numbers there, you get 902. But that 902 comes from the root, but it's not actually just B, L, N, M, E, B, because as I said before, from N to M is actually from N to L to M, and from E to B is actually E to L to B. So if we want to give the nodes that we're visiting, see that we actually go from B to L to N to L to M, and then from E to L to B. So the solution is different from the classical problem again in that we're visiting some of the nodes more than once. We can find a lower bound by first of all deleting B from our matrix, and then considering an algorithm to calculate the minimum spanning tree of the residual network. So this time we're going to be using Prim's algorithm, and so starting Prim's at E, then you can see that the shortest one there is 148. That gives us added in L. Now we need to look at both columns now, 1 and 2. So the shortest one then is 110. That gives us N being added in as our third one. Sorry, L's scrubbed out. And N is now ruled out. But we've got 3 columns to look at. And the next shortest or least weight is the 126 in there. We've then got to add in B using the 2 shortest arcs that are available, so the 82 and the 102. So therefore our lower bound solution is the minimum spanning tree, so the minimum spanning tree, or what's called the residual minimum spanning tree, and that's of size 148 plus 126 plus 110. And then that gives us a value of 384. So that the lower bound is equal to 384 plus the 82 plus 102, giving a total of 568. Now this is not actually a tour, remember, so this is not going to be a solution, but it gives us a lower bound. So we're not really worried about which nodes we're visiting because it's not actually a tour in itself. We just know that the optimal tour will be greater than 568. So we can put those 2 things that we found together and say that if this was time, then the time taken in our tour would be somewhere between 568, be less than t, which will be less than or equal to 902. So the optimal value is somewhere between 568 and 902. So just going over that then in a summary, we first of all start off by turning the practical problem into a classical one, and we solve this new problem. But when having solved it, we must remember to check the solution against the original network to find out which nodes are visited. And some nodes in the real network will be visited more than once, or may be visited more than once. We could, as before, try using every node as a starting point to see whether there is another solution, or a shorter solution for the upper bound and the lower bound. However, that becomes rather tedious. And we can draw conclusions, as we said, about the upper and the lower bounds, and trying to see whether we can get those closer together. Well, that's the end of this video, and indeed the end of the section of Graphs and Networks 2, where we were looking at the travelling salesperson problem.